Right. So let's get started here. So welcome everybody to this month's STEMS webinar. So we are very happy to have Byrne as our speaker today. So Brendan is currently a senior data scientist at Qube Technologies, which is a Canadian company that focuses on greenhouse gas emissions, and he's actually working there on monitoring methane emissions. He holds a PhD from the University of Toronto. During that time, he started working on these atmospheric inversions, and that eventually brought him to JPL, the Jet Propulsion Laboratory in Pasadena, after his PhD. And he spent several years at JPL working on the global carbon cycle and its implications for climate change. He did very important and high-profile work there, especially on these flux inversions, so basically how you take atmospheric observations and use those to infer carbon fluxes and other greenhouse gas fluxes. And that led to very high impact work. Like, for example, this summer, he led a Nature paper on the carbon emissions from the 2023 Canadian wildfires, which received a lot of attention from the global press. So we are very fortunate to have Brendan here with us today, and he'll be talking to us about sort of the details of how and the kind of the methodological aspects of how these atmospheric inversions are done. So the title of his talk, you can see here, is Quantifying Greenhouse Gas Emissions Through Atmospheric Inversion Systems. And with that, Brendan, please take it away.
All right, yeah, so thanks very much for inviting me. I'm very happy to be here and giving this seminar. So yeah, let me know if anything goes too wrong with my audio or anything like that. But so I'll get started here. So yeah, I'm going to give a relatively high-level overview of these inversion systems that all kind of follow this general process. So they intend to use atmospheric concentration measurements to quantify sources and sinks. So kind of the basic concept here is that you measure an atmospheric concentration. So in this image, you see smoke coming out of a wildfire, but you also have carbon monoxide and carbon dioxide coming out of this wildfire, or you have carbon dioxide coming out of a coal power plant. And you measure the concentration downwind with the objective of estimating what the fluxes were that caused your observed concentration through a forward model, which is like the atmospheric transport. And so that's kind of the general idea behind this approach. In this talk, I'm going to introduce kind of how the general kind of high level of how these types of inversions are done through a case study looking at the 2023 wildfires that came out, as was mentioned in Nature a little while ago. And then, so both how these inversions are done and how these results are used with other data sets to kind of understand, processes and what exactly, is happening with these big events like Canadian wildfires. And then I'm going to highlight some other applications, including these large-scale carbon monitoring, such as kind of national carbon budgets, and then monitoring of kind of smaller scale stuff, such as I'm doing now, looking at kind of oil and gas methane leaks. So, for anyone not aware, summer of 2023 saw this really extreme wildfire season across Canada, the worst wildfire season on record. It's had a lot of impacts. There was a lot of evacuations occurring during the fires. There was a lot of air quality impacts. New York City was briefly had like the worst air pollution in the world from smoke coming down from these fires. And the fires were known to have emitted a bunch of carbon to the atmosphere through this burning, but it was really uncertain how much was coming out of them. And that was kind of something that we see these top-down inversions could provide some information for. Okay, so in this study, we really want to look at the amount of carbon emitted from the fires. And then, in addition to just estimating these fluxes, looking at climate context and implications and lessons from events like this. Okay, so when you're looking at an event like a wildfire, there's kind of a few ways to, or maybe two distinct methods for tracking emissions. One approach is called a bottom-up approach, where you basically try to model more of kind of like a process model from the small scale to get aggregate large scale results, large scale emissions. And this is done in a couple ways. It uses generally satellite data of either burned area or fire-rated power. So here on the left, you see burned area. This is coming from something like MODIS, where you see differences in reflectance from land that's not burned and burned. And from that, you're able to map out what area is burned. Or you also have fire-rated power. So, fires give off heat, thermal energy, and you're able to see that from space. And so what you do is you take either this burned area, this fire-rated power, and you basically model what the emissions would be from that observation. So you have something like burned area times the amount of fuel, so like the amount of carbon that was stored in that area that burned, and then like the fraction, so the fraction was consumed, and then the fraction of the consumed carbon that was emitted as the gas, a certain gas, like all of carbon or carbon dioxide or carbon monoxide. And with radiative power, you have a similar approach where you have the total radiative power measured, you multiply that by a combustion rate and an emission factor. And there's a variety of different databases that use these approaches. GFED uses this burned area, and then GFAS and QFED use this fire radiative power. And these are great. They give really high resolution results, but they're often they often contain a lot of uncertainties. So it's there's a lot of uncertainties that go in both in the measurements. Like it's hard to see all burned area, but also things like fuel consumption and emission factors can be quite uncertain. And so that is why these top-down or these atmospheric inversions are useful for potentially refining the emissions that you get from those types of estimates. And I'm going to go through here the general process for these fires that we use to estimate the top-down emissions, basically starting with the prior estimates, which was these bottom-up data sets. So you basically start off with your prior, which is coming from one of these bottom-up data sets here. So you have this set, this X prior, which is the set of emissions that are being released. You then have an atmospheric transport model, which simulates how the atmospheric composition. So in this case, for this study, we look at carbon monoxide, which is good for looking at fires. And so you basically simulate how that's going to move in the atmosphere. So your rate of change with time is basically the divergence of the winds. So you have V, which is this wind vector, usually coming from some kind of pre-existing reanalysis data set, is equal to the fluxes. So you put those fluxes in, you take winds, typically from reanalysis data set like NERA, and you transport what the concentrations would be in the atmosphere. The next step is you have some observing system observing the real atmosphere. So in this study, we used TRPOMI, which looks at reflected sunlight. And so it backs out how much carbon monoxide is in the atmosphere from these observations. This is itself an inverse problem, but I'm going to kind of skip over that for this. So you then have Y, which is your observation of the atmosphere coming from this instrument. And then you also have, you can simulate what your expected Y is. So here, just taking the prior fluxes, we have H, which is this transport of the emissions through the atmosphere and into the observation, which is linear. So we have, it's ignoring chemistry, it's linear. So we're able to basically look at our real observation and what we simulate our observation to be given the bottom-up data set we've put into our model. You can then create a cost function here we create like a Bayesian cost function that weights the observations we have with uncertainty on those observations and prior information we have with uncertainty we have on the priors. And then if we minimize this cost function, we generate a maximum a posteriori solution. And so this allows us basically to take these measurements of atmospheric concentration and optimize surface fluxes. There's, in practice, a variety of different methods that can be used here. So you can analytically provide a solution, or you can use numeric methods. 4D VAR is the name of the method we use, but I'm not really going to dive into those specifics. All right, so yeah, we perform this top-down analysis to get these updated estimates of the emissions, or posterior estimated emissions. And we basically make that agree with the atmospheric concentrations. We update them to be more consistent with the atmospheric concentrations within uncertainties. So this is showing kind of a general idea of what the carbon monoxide concentrations look like over Canada that summer. So you can see for the summer 2023, you have this big enhancement in carbon monoxide basically all summer over Canada because of these really long-lasting fires. If we then look at the observation minus the model, so the difference here, we can see that this Qube prior, when we put that in our atmospheric model and simulate the observations, we really underestimate the concentrations. So our observations are much higher. They're all red here. And then we perform our inversion and we get a set of concentrations which are much more in agreement with the satellite observations of carbon monoxide. So that's kind of general high-level outline of the approach. Now I'm going to get into the results of what we actually saw for these fires in Canada. So just, based off the carbon monoxide data themselves, this is what a summer looks like averaged over 2019 to 2022 over this region. And this is what it looked like in 2023. So you could see already that there was something very unusual happening over Canada with these very large concentrations that we don't see kind of on average. And then we can translate that into emission estimates. So what this plot is showing on the y-axis here is a CO2 plus CO. So basically the total carbon emissions over May through September for Canadian forests. The shaded area is showing previous years, and this on the right is showing 2023. Now, each of these bars on this part are showing for the bottom-up estimates. As I mentioned, there was these variety of bottom-up estimates that sometimes diverge a bit because of assumptions you have to make. And so you see GFED, GFAS, and QFED result in quite this large spread of estimates. And then in 2023, for the top-down estimates, we see here our estimates using the atmospheric concentration data, we're able to revise these bottom-up estimates to a much narrower range. And so we're able to assess the emissions to 570 to 727 teragrams. Now you can similarly look at these bottom-up estimates and top-down values for the previous 22 years here, from 2010 through 2022. And you can see that the emissions in 2023 were way bigger. These are showing the distribution, so the box and whisker plots of the emissions from different years using both bottom-up and top-down. But, you may be thinking, well, what is 0.6 petagrams carbon? So the easiest way to contextualize that is to look at fossil fuel emissions from countries. And so this is comparing the 2023 emissions from the Canadian wildfires to carbon emissions from large countries. And these are fossil fuel emissions over an entire year and relative to the fire emissions from May through September 2023. And what we see here is that these fire emissions, if they were a country emitting carbon, fossil carbon, they would have ranked fourth. So only China, the US, and India had larger fossil fuel carbon emissions than the total carbon coming from these wildfires. So this was really a large event in comparison to kind of fossil fuel emissions that occurred over a pretty short time span, over a pretty short, small area. Well, not that small, over Canada. Right, so, these top-down inversions are, I think, are quite useful for narrowing, getting these estimates of the emissions, but also, we wanted to understand, why we see these emissions and what kind of general lessons we can learn about what's happening to these ecosystems. And so another thing we did in this study was we examined the climate context. So why did we have these giant emissions in 2023 when we didn't see these giant emissions in historical years? And right away, 2023 jumped out as being both the hottest and driest year for Canadian forests in the reanalysis dataset, MIR2 datasets. This goes back 44 years. And what these plots on the left are showing is the left is showing the maps of the anomalies, and the right is showing time series of the integrated values over Canadian forests for 2023 and then the preceding 20 years. And so when you look at so the top row is showing the precipitation anomaly. So this is January through September anomaly in precipitation. The second row is showing the anomaly in 2-meter temperature. The third row is showing vapor pressure deficit anomaly. This is something basically closely associated with fire activity. It's like the atmospheric thirst, more or less. And then the bottom is showing the fire emissions from one of the bottom-up data sets from the GFED dataset. And so right away, you can see this was extremely dry year, basically all over Canada, extremely hot over Canada, these regionally very high vapor pressure deficits, and then you have these really large fires. You can see that again in these time series where it's very dry, very hot, and you get these really extreme fire emissions. Two areas really jumped out. Northern Quebec was extremely dry and also quite hot, and the Great Slave Lake area was extremely hot and also quite dry. But really, this was really widespread, this event. And this is showing basically the same data in a different view. So this is showing the top here is showing the precipitation across all Canadian forests from January through September for each of these years shown on the x-axis. And then the second panel here is showing the percentage of the area of Canadian forests that falls in these different Z-score domains. So the red is showing if the precipitation is more than 1 standard deviation below average. Orange is between 1 standard deviation below average and the mean. And the light blue is more than 1, or up to 1 standard deviation above average. And then the dark blue is more than 1 standard deviation above average. Now you can see kind of 2023 relative to the previous years. And then, so I'm going to add on here just the same plot, but for temperature, for 2-meter temperature. And so we see this precipitation deficit, this dryness, was really widespread. 86% of the area was below average in precipitation, and 52% of the area was more than 1 standard deviation below average. And for temperature, 100% of Canadian forest area was above average, and 88% was more than 1 standard deviation above average. So we had both really intense and really widespread heat and dryness. And kind of the last component of this study was to look at the relationship between fire and climate. And so, here we're trying to ask how, what are the implications of the fact that we had this really hot, dry year and we had these really extreme fire emissions? What can we say about the future, and what can we say about these conditions? So this plot is taking the data for the Canadian forest, and basically we grid up the Canadian forest, and we give over the past 44 years, And for each summer, we have a May to September temperature Z-score, January through September precipitation Z-score, and then a fire emission. And then we bin up this data and we calculate the average fire emissions that you get when you're in a specific particular temperature Z-score threshold and precipitation Z-score threshold. So what we see in the historical data is if you have basically high precipitation and low temperature, you end up being kind of in the lower area of the fire emissions shown in this bottom right quadrant. If you have dry conditions and low temperatures, you have a bit more fires than the first category. And if you have high temperatures and high precipitation, you also have kind of a bit more fire emissions. But when you have low precipitation and high temperature, you're in the highest kind of fire condition area. And particularly when you get above like 1 sigma above average temperature and 1 sigma below average precipitation, you get really much more fire occurring. And so this, I mean, this is probably not particularly surprising to anyone that hot, dry conditions have more fire happening, but this is just trying to plot these conditions on a grid. And then what we can do is we can compare the mean conditions seen across years to this this plot. And so, and if I'm losing anyone, please just interrupt and ask a question. So the next thing we add on here is each year we put the mean condition, so the mean precipitation Z-score and the mean temperature Z-score. And so for each year from 2003 to 2022, you can see these black X's. And then for 2023, you see this red X. And so what we see is that basically consistent with the analysis showing this really extreme precipitation and temperature for 2023, we see that that year was way outside the historical range for the previous 20 years in terms of temperature Z-scores and precipitation Z-scores. And so that's, provides good evidence for why we saw such extreme fire emissions for this year. Now, the next thing we can do is we can take a climate projection model. So we have the CMIP, which is an ensemble of climate models that project out how the climate will change under different emission scenarios. And so we take one of the scenarios, which is SSP 4.5, which is kind of the middle of the road climate change scenario, and we put the mean precipitation and temperature Z-scores relative to 2020 to 2020, or 2000 to 2022 on this plot. And so you can see this is kind of the mean conditions for the 2000s, 2010s, 2020s, 2030s, 2040s, 2050s, 2060s, 2070s, and so on. And basically what we see here is that, we have this strong trend in temperature across decades. And by the time we get to the 2050s, we're seeing temperature conditions on average that are similar to this year. So we're going to see much warmer conditions, which are potentially going to make fire events like this much more common. And the precipitation trends are much less clear and much less robust across the ensemble. So I think there's a lot of uncertainty in how we'll see precipitation change going into the future. But this, in this study, what I wanted to really show here was both how we do, these top-down inversions and how we use those estimates to understand both what's happening in the carbon cycle and what's driving what's happening in the carbon cycle. So the main conclusions of this study were that the 2023 Canadian forest fires released 270 to 727 teragrams of carbon. And this, when you compare it to fossil fuel emissions, would rank just after China, US, and India in terms of annual totals. This event didn't happen in a vacuum. It happened during the hottest and driest year in the near 2 record, which is really the period where we have good satellite data. And when we look to the future, these temperatures are going to become basically the norm within a few decades. And so, we can expect to see really big changes in the carbon cycle of Canadian forests, although I think there's a lot of uncertainty in exactly what will happen as these kind of temperature changes will impact fire, but also all kinds of other aspects of these forests. Okay, so that's kind of one very specific case study went over, and now I just want to highlight some other ways these atmospheric concentration data are used. The thing actually I spent most of my time at JPL during my PhD working on was atmospheric CO2 inversions. So, carbon dioxide is kind of the main thing. We're trying to prevent increases in atmospheric carbon dioxide to limit climate change. And if you look at basically the human emissions, so this plot on the right is showing the CO2 emissions above zero. So this is through land use in yellow and through fossil fuel emissions in gray over time. And then below zero is showing where these emissions end up. And, even though we're emitting all this stuff to the atmosphere, only about half of it ends up staying in the atmosphere. And, we think that the rest of it is about evenly distributed into the ocean. So it goes through partial pressure difference, goes into the ocean. And also we're having carbon taken up in land ecosystems, which is partially due to reforestation, partially due to increasing atmospheric carbon dioxide, which it's called CO2 fertilization. But actually, to a large extent, we don't really understand why and where this is happening. And so, if we look towards the success of the Paris Agreement and, success in terms of limiting the rise in atmospheric CO2, we both need to know exactly where the fossil fuel is being emitted and where that carbon being emitted through anthropogenic activities is going, which are not super well understood at the moment. So I'm going to show basically an image here of atmospheric carbon dioxide and how all these different sources and sinks impact concentration. This is a nice visualization from recently made by NASA. So what you can see, first of all, is that to a large extent, you're looking at weather. You see carbon dioxide is a pretty long-lived thing in the atmosphere, and so it really blows around. So this atmospheric transport that I talked about earlier is really important. This is, I think, showing the winter. So another thing that really pops up here is urban areas. You have these small little point sources that are pumping out carbon everywhere, wherever there's people. And but the other aspect is that there's this really widespread biosphere that is taking up carbon during the day and releasing it at night. And this is, as we kind of zoom around the world, you can see the biosphere effect, where it's absorbing carbon during the day, releasing it at night. And this also has a really strong seasonal effect. So in the summer, in the northern hemisphere, a lot of carbon is taken up and then released back to the atmosphere. So there's tons of different processes that are going on that have big impacts on carbon dioxide. And so what the atmospheric CO2 data really allows us to do is work backwards and get kind of net budgets, like the net release due to fossil fuels and ecosystems and all these different things, so that we can look at the totals of carbon being taken up or released regionally across the world. And so this was a paper I led, but it was had really large contribution from people in this community, especially around the CO2 mission, which is a NASA mission measuring carbon dioxide. And so in this paper, we estimated carbon dioxide budgets, so national carbon dioxide budgets for countries around the world. So what you can see on the top right here is our top-down estimates of the net surface emissions and removals. So brown is showing a net release of carbon, and green is showing a net uptake of carbon for countries around the world. This net effect can be broken down into a fossil fuel component. So you can see, no one's absorbing fossil fuels, everyone's releasing fossil fuels. And so you have, surprisingly, the US, China, the biggest emitters, and India. here, and then the bottom is showing the net terrestrial carbon stock change. So this is basically how much the biosphere is taking up or releasing. And as I mentioned before, we know that about a quarter of the fossil fuel or anthropogenic emissions are ending up in the biosphere. So we can see that in general, across countries, it's taking up carbon. So we did this by actually doing a bunch of different inversion systems. These atmospheric inversions I mentioned before can be subject to biases and uncertainty due to systematic errors in things like getting the atmospheric transport wrong, decisions about how you implement the inversion, and things like that. And so we take an ensemble of these inversions, kind of the same way climate projections use ensemble models, and we look across that ensemble for more robust features and for quantifying uncertainties. We find that, as things are now, we can estimate pretty robust sources, signals for large countries such as like the US, China, or Russia, but it becomes challenging to isolate smaller countries such as like the European countries. And, as you can think in that visualization I just showed, you can really see that a lot of what you see in atmospheric concentration measurements are these swirling of the carbon dioxide in the atmosphere. So really isolating sources from the mixing and weather transport you see is pretty challenging. And this is just kind of highlighting, so, I think these atmospheric CO2 inversions have shown themselves to be useful, but there's some pretty big challenges in really refining them and understanding carbon budgets for smaller countries. The requirements in measurement accuracy and model accuracy are really stringent. Even pretty large scale fluxes across like entire countries basically have a pretty small imprint in atmospheric CO2. So you're really sensitive to biases in both the measurements and in the model, your ability to model those measurements. And that's kind of a real, I think, limiting factor at the moment that people are working on. The other thing is just that, as you saw in that visualization, there's really rapid atmospheric mixing. So in general, you have to regularize the problem pretty strongly without having like extremely dense data. And so maybe, new missions like the CO2M constellation of 3 greenhouse gas observing satellites might, help this to an extent, but it's also just, a very challenging problem given the relatively small imprint that local sources and sinks have on concentrations. So I think, as I mentioned here, a lot of these global inversions are most useful. I'm not sure how to get this. So I was trying to get that to run again, but they're most useful actually for looking at aggregate large-scale fluxes that come from the biosphere, because the global inversions generally are pretty coarse. So they're like 400 degrees by 500 degree grid cells, so really coarse grid cells, like on the size of some countries. And on that kind of scale, the biosphere actually, like forests, from day to day have quite a large impact on the concentration, and those are also the fluxes that are generally most uncertain. So from an information perspective, these large-scale inversions are generally most useful at informing what's going on in the biosphere, these large-scale sources and sinks kind of in this bottom right plot here. But the other thing we need to track is fossil anthropogenic emissions. Here I'm going to focus for CO2, but also for methane. There was this global methane pledge recently that really has put the focus onto methane, to which extent we're aiming to reduce global methane emissions by 30% from the 2020 levels by 2030 is really kind of the most immediate step we can get to trying to reach 1.5 or 2 degree warming. And a lot of anthropogenic emissions are different than the biosphere in that they happen over pretty localized areas, small areas. And this is showing the methane emissions. Big sources are landfills and also things like oil and gas facilities. And as was mentioned, I left GPL a couple months ago to join Qube Technologies, which is a private company looking to provide ways to inform these methane emissions and continuous monitoring of leaks and different methane sources, so that actions can be taken to reduce those sources. And so the way we do this is that we've developed these low-cost methane sensors. So this is an example shown here. Is a sensor that is methane, a solar panel, and then like wind measurements. And you can put these sensors, spread a number of these sensors around a given facility. So for example, here, you could put these sensors all around the perimeter. And then you can continuously track the emissions here. So this is showing kind of the methane concentrations, and you see these spikes, so you can see something's happening there. And so this, my role here and what we're doing is using inverse systems. So the same method as I mentioned before for the fires, but really at a smaller scale, looking at these plumes coming off these sites, and then using our methane measurements and meteorological measurements to back calculate where that's coming from. And so, some of the different challenges that come with this is that these inversions at meter scales, facility scales, have different challenges than the kilometer or 100-kilometer challenges in representing atmospheric transport on the large scale, but there's still real challenges with getting the atmospheric transport right for relating fluxes to concentration. Another thing that's really important here is that action needs localization. So if you want to fix a leak, you need to understand exactly where that leak is coming from. And so that's another thing that I'm working on here. And that's, I guess I'm ending a little bit early here, but I put my contact information below here. We're a private company, but we are really happy to connect and work with academia in the research community. And so, feel free to contact me if you have any questions or if you want to have any ideas for connecting. So yeah, I'll leave it there. Happy to answer any questions or open to discussion or comments. So thanks very much.